It was the year 2012 when researchers found something really exciting in the solar wind. They found evidence that indicated that our sun ejects material to space at an incredible speed. It's not only that, but they also learned that this is a continuous process and that it happens with other stars as well. This ejection of elements from the sun or any other star is known as stellar wind. It's a flow of charged particles, mostly protons and electrons, which are emitted continuously from the upper atmosphere of a star. The speed of these particles is relatively high, reaching up to several thousand kilometers per second. But that's not all. In addition to protons and electrons, the stellar wind also carries with it heavier elements, including helium and even iron. Now, this may not sound particularly remarkable given that the sun is a ball of burning plasma, but the fact that it can eject iron is indeed amazing. It's because iron is one of the heaviest elements that exists. Yet, it gets ejected into space by our sun, along with lighter elements carried by the stellar wind. But how exactly do we know that? Well, thanks to NASA's Solar Terrestrial Relations Observatory. Also known as the Stereo-A spacecraft, which has been studying the sun since its launch in 2006. The mission of Stereo is to observe the sun from two different viewpoints, ahead and behind Earth in its orbit. This provides a three-dimensional view of the sun and helps scientists track phenomena, such as coronal mass ejections, CMEs, which are large-scale eruptions of plasma from the sun's corona. In January 2012, Stereo-A spacecraft provided a close-up view of an event that left scientists scratching their heads. What they observed was a cloud of heavy elements, mostly iron, being ejected from the sun at incredible speeds. But here's the real head-scratcher. The ejected iron was not present in the sun's corona. It was instead found in the streamer, a large and stable coronal mass ejection that had been released about 4 days prior to the observations. This finding was like stumbling upon a needle in a haystack. It showed that the sun ejects iron into space, but only in very small amounts and during specific events like CMEs. What makes this discovery so significant, you might ask? Well, hold on to your seats because what we're about to tell you will blow your mind. Iron is a key ingredient in the creation of planets, stars, and galaxies. Without it, life as we know it would not exist. But there's a catch. Our planet has plenty of iron, but it doesn't just lie around waiting to be picked up and used. In fact, getting access to this vital resource can be quite challenging. That's where meteorites come in. These space rocks are like time capsules that preserve ancient materials from the early solar system. And thanks to the study of meteorites, we now know that the majority of iron in our solar system originated outside the sun. This raises a fascinating question. How does iron and other heavy elements find their way onto Earth? The answer lies in understanding how the sun and other stars produce these elements in the first place. Stellar nucleosynthesis is the process by which elements are created inside stars through nuclear fusion reactions. Our sun, for example, produces helium by fusing hydrogen into helium in its core. But as the sun ages, it will eventually run out of hydrogen and begin fusing helium into heavier elements like carbon, nitrogen, and oxygen. These elements are produced in the star's core and are ejected into space only when the star goes supernova. So where does the iron in our solar system come from? The answer is shockingly simple, but also incredibly mind-blowing. It comes from the remnants of exploded stars. But wait, let's take a step back and simplify this further. Stars like our sun are not born equal. They have different masses, which significantly impacts their lifespan and eventual fate. Massive stars, several times larger than our sun, live fast and die young. On the other hand, smaller stars like our sun have a much longer lifespan, but also die more slowly.
Wow.
When massive stars die, they explode as supernova, creating some of the most spectacular and luminous events in the universe. These explosions release huge amounts of energy and matter into space, creating beautiful and intricate structures known as supernova remnants. But it's not just the explosion that makes these stars special. It's what happens before. As the star runs out of hydrogen, its core begins to collapse under its own gravity. This creates a core-collapse supernova that ejects the star's outer layers into space and leaves behind either a neutron star or a black hole. Its collapsed cores are the most compact and dense objects in the universe, and they play a crucial role in the production of heavy elements. On the other hand, smaller stars like our sun don't explode when they die. Instead, they shed their outer layers, forming beautiful planetary nebulae and leaving behind white dwarfs. White dwarfs are the final stage of low-mass stars like our Sun, and they represent a unique opportunity for studying stellar evolution. But why are these exploded stars so important in the production of iron? Let us explain. The intense heat and pressure in the cores of massive stars allow for the fusion of elements heavier than helium. For example, in a massive star, silicon can be fused into iron. This process of fusing elements into iron is called the iron catastrophe, because it marks the end of a star's ability to generate energy through nuclear fusion. When iron builds up in the core of a massive star, further attempts to fuse it result in the absorption of energy rather than the release of energy. This leads to a runaway collapse of the star's core and the explosion of the star as a supernova. This explosion releases enormous amounts of energy and matter into space, enriching the surrounding interstellar medium with heavy elements such as iron. In contrast, smaller stars like our Sun do not experience the iron catastrophe. As a result, they do not produce iron in their cores. Instead, iron is produced in the atmospheres of these stars through a process called the iron factory. This occurs when hydrogen from the star's atmosphere is accreted onto its surface and then fused into helium. The resulting energy release heats the surface of the star, allowing iron atoms to escape from its gravitational pull. But if iron is not produced in the cores of smaller stars like our Sun, how did the iron in our solar system originate? The answer lies in the winds of these stars. When iron atoms escape the gravitational pull of a star, they become part of the stellar wind, a stream of charged particles that flows away from the star. Over billions of years, the iron carried by stellar winds has accumulated in space, forming a vast reservoir of this valuable element. In fact, the majority of iron in our solar system is believed to have originated from the winds of low-mass stars like our Sun. But that still leaves us with a big question. How does iron get from space onto Earth? The answer is meteorites. These space rocks contain a record of the early solar system and provide clues to the origins of our planet. By studying the composition of meteorites, scientists have learned that the majority of iron in our solar system came from outside the Sun. This means that the iron in our planet likely arrived on Earth via meteorite impacts in the early stages of its formation. One type of meteorite that provides clues to the origin of iron is called primitive meteorites. These meteorites are believed to be some of the oldest objects in the solar system, dating back to the earliest days after the Sun formed. By studying these meteorites, scientists have discovered that the iron-to-nickel ratio is the same in both the meteorites and in Earth's core. This suggests that the iron in Earth's core came from the same source as the iron in primitive meteorites, namely the stellar wind. But it's not just meteorites that provide evidence of iron's extraterrestrial origin. In recent years, scientists have developed new techniques to analyze the isotopic composition of iron in meteorites and in terrestrial samples. Isotope analysis can provide insights into the origin and evolution of elements in space and on Earth. And the results of these studies have been surprising. The isotopic composition of iron in Earth's core differs from that of iron in the Earth's mantle and in meteorites. This suggests that the iron in Earth's core may have a different origin than the iron found in meteorites. However, further research is needed to fully understand this discrepancy. Overall, the evidence overwhelmingly points to the fact that the majority of iron in our solar system originated outside of the Sun. This iron was produced in the winds of low-mass stars like our Sun and was later transported to Earth via meteorites. The discovery of iron in the solar wind and its ejection from the Sun was a significant breakthrough in our understanding of the Sun and its activity. It also provides valuable insights into the origins of iron in our solar system and on Earth. Studying the Sun and its activity is crucial for understanding its behavior and predicting its future. As our knowledge of the Sun grows, so does our understanding of its impact on our planet and the solar system as a whole. And who knows what other fascinating discoveries await us in the near future. Maybe we'll learn that the Sun has even more tricks up its sleeve, like ejecting other heavy elements or even exploding one day. Only time will tell.